Next, we're going to look at another type of tracer that's used in a special type of scan called a PET scan. And here the way the tracer works is just a tiny bit more complicated. PET scans are used to look for very hungry cells. So remember, that's areas of the brain that are much more active than other parts, or cancerous tumours which are growing much faster than surrounding cells. PET stands for positron emission tomography. You don't need to remember that, and tomography is just a fancy word for picture. Remember that these scans are all about imaging what's inside the body. Okay, so just as with the normal tracer, your patient will ingest the radiopharmaceutical. Remember, that means radioactive drug. In this case, though, it's usually fluorine-18. So this is a radioactive isotope, but the unstable nuclei of this isotope decay by emitting positrons. So let's say you're imaging somebody's brain. Once again, the radiopharmaceutical is going to be taken up by the hungriest cells the most. So let's say that this area of the brain here is very active. It's going to take in a lot more fluorine-18 than the surrounding cells. So we're going to collect fluorine-18 nuclei in this part of the brain. Now, when one of those nuclei decays, it's going to emit a positron. I'll just write it here so you can see that. Will be our symbol for the positron. But remember that this is an antiparticle. It's the antiparticle of the electron, and when a particle and its antiparticle meet, they annihilate. So these positrons that are being emitted in this part of the brain, they are going to meet electrons virtually immediately. As soon as they meet an electron, they're going to annihilate. And when they do that, they create two, and in opposite directions, two gamma photons. From now on, a PET scan is just the same as a normal gamma tracer. You will have gamma cameras around the outside of the patient, and these will detect the two gamma photons coming off, and these will, by tracing back the line of where those gamma photons came from and how long it took them to get there, you'll be able to work out where the decay happened. Okay, so here's a question on a PET scan, and then the second part there is a bit more nuclear revision. Right then, let's see how you did. So for part A here, for the first mark, fluorine-18 collects in the area of increased activity. For the second mark, it emits positrons, and these positrons annihilate with electrons. For the third mark, each annihilation results in two gamma photons travelling in opposite directions. You must specify that they travel in opposite directions. And for the fourth mark, the times that they arrive and the directions are used to locate where it was that they were emitted. A possible alternative fourth mark there is that you have gamma cameras around the outside of the patient to detect the gamma rays. And for the second part, we're talking about activity. So I'm going for this formula here. And we're asked to calculate the time when the activity has decreased to 30% of its initial activity. Now, its initial activity is A0. So the activity we want is 30% of A0. So we want to know, when is A 30% of A0? It's up to you how you want to do this. I'm gonna write it like that, but however you want to do it. Oops. There we go. So we're saying, when has the activity become 30% of the initial activity? Okay, now we need to know, that's our first mark there. Now we need to know what the decay constant is, and we remember this tiny little formula that often gets forgotten. it's that one. And so that allows us to work out what the decay constant is. Now, in fact, we can leave the half-life in minutes, and then we'll have minutes to the -1, and then our final answer for T will come out in minutes as well, which is what we want. So that's actually a quicker way to do it. That's how I'm going to do it. But if you did convert to seconds, then you'd end up with seconds to the -1, then you'd end up with seconds at the end, and convert back to minutes. Obviously, you're going to get all the marks there. Okay, this is our second mark then, getting our decay constant. And then finally, working through the calculation, we get 190 minutes.